You've probably heard that quantum mechanics is more than just a little crazy, but as someone with an actual degree in that thing, let me set the record straight. This is absolutely correct. Now, even in this entire field of craziness, one thing has always stood out to me: Bell's inequality. Admittedly, this does sound unassuming, and most people probably have never heard of it before. Anyway, one of the most unappealing qualities of quantum theory is that it cannot give you clear predictions of outcomes, only probabilities. Many people, including Einstein, did not like this, and they came up with the idea that maybe beyond quantum mechanics there is another structure that is deterministic and where things make sense again. We just haven't penetrated down to that layer yet. This whole idea is called hidden variables because where we now only see randomness, there might in reality be a hidden mechanism. The analogy here is that yes, we can describe a coin toss as a 50-50 random outcome, but in truth, there are many different forces, accelerations, directions and angles that do determine what happens to the coin. So at least in principle, it is predictable with absolute precision. What Bell managed to do with his inequality is to come up with something that can be measured in an experiment, and the outcome will tell us whether these hidden variables exist or not. In a very meaningful way, this allows us a deep measurement of reality itself. And if you don't think that's absolutely crazy, then you're crazy. John Stewart Bell was born in 1928 in Northern Ireland at about the time the so-called Copenhagen interpretation of quantum mechanics was being finalized. When Bell went to university to study physics in the 1940s, this was already being taught. Like many physicists of these early days, he was dissatisfied with some aspects of quantum mechanics. And he was intrigued by the concept of hidden variables when he first heard about it. Well, the idea is certainly very compelling, especially to the kinds of people who study physics and mathematics. What looks like randomness and probabilities on the surface has a deeply hidden mechanism that secretly runs the universe in perfect order. Bell's excitement was short-lived though. The famous Hungarian math genius Jon von Neumann had published a seminal book about the mathematical foundations of quantum mechanics, which contained a proof that hidden variables were impossible. Bell tried to get his hands on this book, but at the time, the only version available was the German original, which Bell could not read. Note that I, as a German native speaker, only have the English version of the book to restore harmony to the universe, of course. It's important to understand von Neumann's reputation back then. Basically, the sentiment was that if von Neumann had proved it, don't even bother looking it up. So Bell did not follow up and moved on to other things. But then, in 1952, David Bohm published his pilot wave interpretation of quantum mechanics. We don't need to go deep into the details here, but the basic premise is that quantum particles are perfectly normal particles, with the addition that they are guided by a pilot wave. And the behavior of this wave is described by the Schrödinger equation. Any uncertainties and probabilities arise just because our incomplete knowledge of the particles. For example, their precise position can never be measured perfectly. Bohmian mechanics was not truly a rival theory to quantum mechanics. It was just a different way to look at the same existing rules, and that's why we call it a different interpretation. It uses all the same equations from standard quantum mechanics, plus some additional stuff, and it also makes all the same predictions. But, and this is the big point in our story here, it contains hidden variables. In Bohmian mechanics, the locations of all particles are always defined, and the velocities, and therefore the momenta, can be derived from those and the wave function. The precise location of all particles cannot be measured, but they do exist in the background. So, contrary to von Neumann's proof, Bohmian mechanics does contain hidden variables, but it still works. Like I said, it gives the same predictions as the Copenhagen interpretation. When John Bell read about this, he was electrified. He said, "Today, I have seen the impossible not just being possible, but being done." And what is proved by impossibility proofs is often just a lack of imagination. He began thinking about hidden variables again, and he read the EPR paper and all the replies to it. And he was determined to get his hands on von Neumann's proof and figure out where it was wrong. In 1960, John Bell moved to Geneva to work at CERN. And there he found a German-speaking colleague who would translate von Neumann's proof for him. The issue that he found wasn't that von Neumann had made a mistake per se, which would have been a scandal, but that simply one of his assumptions had been too strict. And this had made his proof almost circular in nature, so hidden variables cannot exist because hidden variables cannot exist. But Bell achieved much more than just finding this mistake. The way we think about our universe, our reality, is called local realism. This means things exist and have properties whether we observe them or not, and that any interaction between two things can happen at most at the speed of light. Bell managed to formulate a mathematical inequality that assumed these, common sense to us humans, limitations of locality and realism, and got this result. Note that there are many more inequalities that can be formulated to the same effect. All of those are also called Bell inequalities, but might also have additional names. The bad news is that this looks very complicated and mathematical, but the good news is it can be explained in a very simple way. We need three properties that are binary, so they have one of only two possible values. For example, let's imagine there is a group of people with these properties. Their eye color is either blue or not blue. Their hair color is either blonde or not blonde. And they are either tall or not tall. These properties are independent of each other, so people can be any combination of these, which means the bubbles overlap with each other. We're going to look at three specific combinations now. Why exactly those three? Because it works with these. But like I said though, there are many variants of this inequality, so we could work with different choices and get a different but similar inequality out of that. Either way, the three we're going to look at are these: blue-eyed and tall, blue-eyed and blonde, and not blonde and tall. Now, when we add these two together, we get a visualization of Bell's inequality. The combined areas on the right are larger than the area on the left. And not just because of any particular way that I chose to draw them, but because they completely contain the area on the left. This is trivially correct for any type of properties that are fixed. And there is nothing deeper behind this. Bell suggested an experiment where this can be checked. Entangled pairs of photons are emitted and then measured at distant locations. These need to be so far apart that no signal can be sent from one location to the other in time, so that no measurement can influence the other. Now obviously, photons do not have hair or eyes, so the measurements we use are the polarization angles, alpha, beta and gamma of the photons, so basically directions in space. And we count whether a photon was detected, 1, or not, 0. Now if you're unclear what photons are and what polarization is, it doesn't really matter here. Just think of them as some particles with some properties. That's all we're gonna need for now. This leaves us with the following Bell inequality. This is the same as before, just with different properties, in this case angles. If the polarization angle of a photon is a normal property that exists, like blue-eyed or blonde, then this inequality must hold. The interesting bit is that, according to the predictions of quantum mechanics, this inequality is violated. An important part of this is that entanglement introduces an immediate interaction between two particles, so a highly non-local effect. This means that in quantum mechanics, properties of particles work in a different way. And that's the big catch here. If the polarization angles of photon pairs are just a normal property that already exists before it is measured, and if one photon cannot interact with the other, then this inequality must hold. But on the other hand, if quantum mechanics is right and this inequality is violated, then this cannot be squared with local realism in any way. Back to hidden variables. The secret parameters that are supposed to determine the outcomes that quantum mechanics can only give probabilities for. If those hidden variables are supposed to be realistic, meaning they exist independent of and before being measured, and they are supposed to be local, so they cannot influence each other faster than the speed of light, they would contradict quantum mechanics. This result is known as Bell's theorem. There are differences between quantum mechanics and local realistic hidden variable theories that can be measured in experiment. So, if the experiment shows that the quantum prediction is correct, then local real hidden variables cannot exist. Note that Bell's inequality only applies to locally real hidden variables. Other kinds of hidden variables are still possible. For example, the hidden variables in Bohmian mechanics are non-local. They can have immediate effects on other systems, regardless of how far they are away. Now, Bell's theorem was a clear call to action to all experimentalists, but the technical limitations at the time meant that it would take a while. The first experimental test was achieved in the 1970s, and then further developed until the 2010s, when all loopholes were finally closed. These experiments led to the Nobel Prizes in Physics in 2022, and they will be discussed in much more detail in their own video, out soon-ish. Oh, and the results. They were in favor of quantum mechanics. Every single time. Well, it turns out that reality is not as neat and logical as we thought it was. And turns out we can measure that, which is still the craziest concepts in all of quantum mechanics to me. Anyway, as for Bell, he was quite amused by the results. While he had always been a skeptic of the Copenhagen interpretation, he hadn't necessarily doubted the correctness of quantum theory. A quote from him sums this up nicely. Bohr was inconsistent, unclear, willfully obscure, and right. Einstein was consistent, clear, down to earth, and wrong. And after the experiments of the 1980s, the broader physics community had finally caught up with the significance and also the magnificence of Bell's theorem and his inequality. So his name was making the round for a Nobel Prize. We will never know for certain, but it has been credibly leaked that Bell was chosen to receive the Physics Nobel Prize in 1990. So he wasn't just nominated, but he had actually been selected as the winner. It was to be announced on October 9th, but sadly, on October 1st, John Stewart Bell passed away due to a cerebral hemorrhage.